The Simon 8.4, L'Hopital's rule, used to take and evaluate limits when we have an indeterminate situation. So either 0 over 0, infinity over infinity, or plus or minus infinity. Let's go through it. So it's a great tool to have to evaluate a limit, to know L'Hopital's rule. So the first step to any limit is it's a substitution question before you do anything else. So when I look at number 1, the first thing I should do for this limit is understand it's a substitution question. If I substitute in and I can't evaluate it, then I need other tools. So if I substitute in, I get 4 squared subtract 4. That's 0. And then 2 plus 2, that's 4. And 0 divided by 4 is an answer. That's not undefined or anything like that. The answer is 0. Done. Number 2. So again, the first step is to evaluate. And usually you can evaluate in your head to recognize what it is to begin with. So if I look at question number 2 and I substitute 1 in for x, first of all, I'm going to separate this. So as soon as I see if I substitute 1 in the denominator, that's clearly 0. I'm going to separate the numerator and denominator because I don't want to get into writing 0 over 0 because mathematically that's not equivalent. 0 over 0 does not equal this. So we don't need to write something that's not accurate. So if I write down 0 divided by 0, the AP exam, the writers, the ones that graded, do not want you to write down 0 over 0. So we're not going to do it. So we're going to write down the numerator and recognize, and then write down the denominator. And this is how we'll show what we're doing. So the limit as x approaches 1 of the numerator, that answer is 0. The limit as x approaches 1, is it? Let me just make sure. Let's not just assume. So 1 take away, that's actually if I plug in positive 1, what is it, positive 2x? And I just wrote it down wrong. That's what confused me. So positive 2x, yes, if I plug in 1, I get 0. If I plug in for the denominator at 0, this shows that it's L'Hopital's rule. So if you take the limit of the numerator, the limit of the denominator, it shows without writing down 0 divided by 0. And now L'Hopital's rule is take the derivative of the numerator, that's 2x plus 2, the derivative of the denominator, which is 1, and now do the same work. Substitute in, and you can see what the answer is. So that's L'Hopital's rule. Number 3. In number 3, you have the limit as x approaches infinity, and it's e to the x over x squared. Now, understand that if we have this situation of the numerator and the denominator, so I'm going to write it as 2 limits, that both of these answers are infinity. So both of these are going to infinity. So as I put in infinity, the answer is infinity. Same thing here. That means the right end behavior is going to infinity for both. So what's the answer going to be? Well, we can then take the derivative. So if we have infinity over infinity, then the derivative of the numerator, so the derivative of e to the x is e to the x, the derivative of x squared is 2x. Both of these are still going to infinity. So if I look and plug it into the numerator, so in other words, if I plug in 110, if I plug in 1 billion, this answer just keeps rising to infinity. Same thing here. So if 2x is a line that's also going to infinity. Both of these are approaching infinity. So I can take the derivative again, and that's e to the x over 2. And now you can clearly see what's happening here. So we're going to learn something in a moment. But for this situation, this is either saying it's going to infinity or it doesn't exist as you're doing L'Hopital's rule. Now, what this is really saying for the right end behavior, when the numerator increases faster than the denominator, then it's going to go to infinity. If this was a reciprocal, if the denominator was increasing faster, then it would be approaching 0. And then if they had the same, if they're increasing at the same rate, you would divide to get the answer. All right, let's look at number 4. So what's the limit as x approaches 0 of x over x subtract 1 subtract e to the x. Make sure I wrote it down correctly. So I'm going to separate the numerator and denominator underneath. So the numerator and the denominator, so I can clearly see what the rule is that I'm going to use. So there it is. I separated it. Substitute in 0 for x. Substitute in 0 for x. E to the 0 is 1. So 1 take away 1 is 0. 0 take away 0. So you can see this is indeterminate by separating them. So how do I evaluate this limit? Is by taking the derivative of the numerator and the derivative of the denominator. So the derivative of 1 is 0, and the derivative of negative e to the x is negative e to the x. So that's a negative and another negative e to the x. Can I now plug in 0? So if I now plug in 0 for x, e to the 0 is 1. So it's really 1 plus 1. So you get your valuation of your limit. That's called L'Hopital's rule. Number 5. In question number 5, the limit as x approaches 0 from the right. So here's a limit situation. It is indeterminate as such, but the absolute value bars, this is going to be one, whenever you see absolute value, to try to graph it if you can. So 5, 6, and 7 are all connected. So the graphs for 5, 6, and 7 are going to be helpful. So whenever I see absolute value bars, I think if it's going to be the graph that's going to help me. So I already wrote down 5, 6, and 7. So how will the graph help me? So what does the graph look like for the absolute value of x over x? So if I plug in positive 1, 1 divided by 1, the answer is 1. And if you look carefully, any positive number I put in, the answer is going to be 1. The only issue is at 0. So at 0, 0 divided by 0 is indeterminate. There's no value there for 0 divided by 0. What's going to happen when I put in a negative number for x? So if I put in a negative number, like negative 1, the absolute value of negative 1 is positive 1, but it's divided by a negative. So because the denominator is negative, it makes a negative answer. So for that answer, all the answers that are negative are going to be negative 1, again, except for 0. So there's the picture of the graph. This is the function, the absolute value of x divided by x. That's what that is, and these are holes. So if I plug in a positive number, the answer is positive 1. If I plug in a negative number, the answer is negative 1. And at 0, we can't have any value for it. It's indeterminate. So what's the limit from the right? So from the right, the limit, the y value, is positive 1. From the left, the value is negative 1. Because they don't agree what the limit is, the limit exactly at 0 does not exist. All right, number 8. The limit as x approaches 2 of x squared subtract 4 and then ln x subtract 1. So step number 1 is to separate the numerator and the denominator and find each limit separately to determine if it's a L'Hopital rule situation. So I need to determine if it's indeterminate. So plug in 2 for x and you get the answer 0. Plug in 2 for x. 2 take away 1 is 1, and ln 1 does equal 0. So it is indeterminate, which means I write the limit notation and now take the derivative of the numerator, take the derivative of the denominator. Now the derivative of ln is draw a fraction. What you see is the denominator. The derivative of that is your numerator. And we could actually make this look a little nicer. You multiply times the reciprocal, or you can plug in 2. So if I multiply times the reciprocal, this is what it's going to look like. So the reciprocal of x, 1 over x minus 1 is that. So now you're multiplying. when you do that, now plug in 2. So 2 times 2 is 4. 2 take away 1 is 1. So it's really just 4 times 1, or 4. Put parentheses around all of it. There you go. Number 9. The limit as x approaches 0, 2 times e to the x minus 1, and then over x squared. So again, we're going to separate it, numerator and denominator. And then solve each one separately. So if I plug in 0 for x, I get the answer 0. And then 0, I get the answer. So this is indeterminate, which means L'Hopital's rule means I can take the derivative of the numerator and denominator. So the derivative here, think of this as 2e to the x, would be 2e to the x would be the derivative. 2 times negative 1 is negative 2, and the derivative of negative 2 is 0, so I don't need it. The derivative of x squared is 2x, and now again I'm going to substitute 0 in. Now I'm not going to separate it because I can see what's happening. So if I plug 0 in the numerator, that answer is 1. If I plug in 0 in the denominator, it's 0. So it's actually 2 over 0. That means this limit does not exist. Do not write down 2 over 0. So we're not going to do that, okay? So don't write that down. Instead, we could write it down separately, but in this case you don't even need to do that, just so that you can see it, but you don't write it as a fraction that is mathematically incorrect. So we can write it down like this, but ultimately the limit does not exist, and we don't write this down for that. All right, number 10. In number 10, it's the limit. Now, the ones that approach infinity are just asking for the right end behavior. So I'm not even going to treat it like L'Hopital's rule. It's just the right end behavior. So if I look at the power terms, it will give me the answer. So the right end behavior here, all I have to do is look at the power term over the power term. So 2x to the 5th, 3x to the 5th. Obviously the x to the 5th divide out, and the right end is 2/3. So it's power term over power term. For number 11, again, it's going to be power term over power term. So the question is the limit as x approaches infinity of 2x to the 4th subtract x squared. Then I have 3x to the 5th plus x to the 4th minus 5x. So the power term on top and the power term on the bottom, that's all I'm going to look at. So the power term on top, the power term on the bottom, and now look at it. Notice the bottom is more powerful. Whenever the bottom is more powerful, it's approaching 0. Number 12, the limit as x approaches infinity, and this one is 3x to the 5th. Oh, it's just the reciprocal, right, of what I just did. And so what would happen then? So for this one, again, if you look at power term over power term, so it's the limit as x approaches infinity, 3x to the 5th over 2x to the 4th. So if the top is more powerful than the bottom, it's increasing faster, more powerful, then it's going to infinity. Or you could also write down it doesn't exist because you can never approach infinity. So either one would be correct. Number 13. Be careful for number 13. So the limit as x approaches infinity, and it's the square root of x squared plus 5 over x. So if I look here, recognize that as you put in positive numbers, the power term here of the square root of x squared is actually x. And it's positive or negative x. But because we're going to positive infinity, it's positive x over x, which is equal to 1. And if you look at number 14, it's the limit as x approaches negative infinity of the same function. And then for this one, when we write it down, because it's going to negative infinity, when you take the square root of x squared, like solving a quadratic, it's the negative x over x for the left side. So it could be positive or negative x, the square root of this, like solving a quadratic. When it's going to negative infinity, it's the negative x. So this one is actually approaching negative 1 when you simplify it. Number 15. So once you catch on to limits, to evaluate a limit is not too bad, and it doesn't take a long time, which is nice. So again, how do you evaluate a limit? Is you do a substitution. And for this one, don't assume that it's indeterminate. So if you plug in 5, 2 times 5 is 10, take away 10. So that's 0 divided by 25, which is just 0. All right, number 16 says use a calculator. I love using a calculator. So the limit as x approaches infinity of x to the exponent 1 over x. So could you use a calculator to do that? Let's see. Let me get my calculator out. So how do I do a limit question here and type that in? So we're going to press menu and calculus, and we're going to go to limit. What number would that be? 4. And then we're going to type in as x approaches infinity. So infinity, if you look here in blue, can you see it? There it is. Can you see that? So press the blue button and then that book. So control and that book. And there's infinity and beyond. This would be if it was a right or left-handed limit, so be a plus or a minus, but we don't have that for infinity, so you can leave it blank. And then here you just type in x to the exponent. Make sure it's a fraction, and it's 1 over x. So control divide makes it a fraction, and then the exponent again is 1 over x, and that's it. So you can see that answer using your calculator. The answer to that is 1. Cool, right? You've been able to use your... Don't you like using your calculator? I do. I'm glad that we have a good calculator we're using, and not an old one that's awkward to use. So here we go again. This is actually the definition of what E equals, believe it or not. That is the calculus definition of what E is. The number E is about 2.7. What's the actual calculus definition of the number E? You just see it right there. So let's type it in so you can see that it's E. So again, we're going to go to menu and calculus. We're going to go to limit. We're going to go as x approaches infinity. And we're going to leave that next box blank. And then inside the parentheses, we're going to type in 1 plus 1 over x, and then to the exponent x. Oops. No, I had to do parentheses from the beginning. Okay, let me do it again. So menu, calculus limit, and then as x approaches infinity again, let me make sure I do it right. Oops, I didn't mean that. And then I'm going to do parentheses again. So a second parentheses, even though I thought the parentheses there would be good enough. 1 plus 1 over x. Move the cursor to the exponent x, and there you go. And notice if you press enter, it just says the answer E. Isn't that cool? That's the definition of what E is, the number E. If you want the decimal to that, oops, that's what E is equal to. But we already answered it. I already answered to it. Isn't that a perfect answer? E. All right, 18. The limit as x approaches 1.5. It's going to just take a moment to type in 2x cubed, subtract 3x squared, subtract 8x plus 12. 6x cubed, subtract 25x squared plus 34x, subtract 15. All right, just take your time and type that in. I'm going to do the same thing. So again, I'm going to press menu and calculus and limit. I'm going to say as x approaches 1.5. Here. And then just going to type it in, move the cursor here, and then do a fraction line. And then in the numerator, 2x cubed, move the cursor, subtract 3x squared, subtract 8x, and then plus 12, and then go, oh yeah, did I type it in right? And then the denominator, 6x cubed, move the cursor, subtract 25x squared, move the cursor, plus 34x, and then subtract 15, and that's it. And you get the answer 7. Just double checking. Yep, and there's the answer. All right, so if you get to use your calculator, that's awesome sauce, right? Number 19. Remember when people said awesome sauce? 19. The derivative is equal to e to the x squared plus 5 times x. And it says find, do the antiderivative. No calculator for number 19. So how would I do that in terms of what I'm doing? So first of all, I need to set this up correctly. So e to the x squared plus 5, the derivative of the exponent is 2x. So it was 1x, now it's 2x, so I need a 1/2. Once I set it up correctly, I can circle the hook and unhook it. And then what's the rule for e is you copy it. So this is 1/2 times e to the x squared plus 5 plus c. Done. Number 20. In number 20, you have x prime at t is equal to 2t subtract 1, e to the t squared subtract t. Oop, where do we go? Here we go. And then what would I do from here? So the first thing I'd recognize is I want to write it calculus friendly to understand what's happening. So how would I write this calculus friendly? So I don't want a fraction. So I'm going to write this as e to the negative of what I just see. So this exponent I'm just making negative, so that's actually negative t squared, and a negative is plus t, but that's it. And then what hook do I need that comes from there? So the derivative of negative t squared is negative 2t, and negative times a negative is positive t, and the derivative of positive t is 1. That's the hook that I need. If I look here, when I do the antiderivative, are they equivalent, right, in terms of it? And no, I need a negative 1 in front, right? Because if I divide by negative 1, they would be equivalent. Then I can unhook it. So the answer needs to start with negative 1, and then just copy. Done. And you could write that as negative t squared plus t if you want to. Oh, and don't forget the candy. Done. All right, number 21. In number 21, evaluate it without using a calculator. So we're just practicing our antiderivatives. These are definite integrals. Now, for number 21, I'm already going to write it calculus friendly. I see 1 over x, and ln x is to the exponent 1/3. If you can see that, then it's easy to do the antiderivative here. So the derivative of ln x is 1 over x. So the hook is there. So the hook is proper, so you can unhook this. And the rule here is just the power rule. So go ln x, add 1 to the exponent and divide, or the reciprocal. And then the limits go from 2 to e. And then the last step is to substitute in. So we got 3/4 ln e to the 4/3 minus 3/4 ln 2 to the 4/3. Now, ln e means 1, and 1 to the 4/3 is 1. So this whole thing is just 1. So it's 3/4 minus, and now there's no way to simplify that at all. So that's what it would look like if you want to see it a different way. Number 22. In number 22, again, it's a definite integral. It's 3 to the exponent negative x dx. So the derivative of negative x is negative 1, so it needs to be a negative in front, so I have to undo it with another negative. So if I multiply it, that's what it is. The rule for an exponential, or the base is not e, copy it. So this gets unhooked, so I have negative 3 to the negative x. And then I need a ln 3 when I do the antiderivative. and then I'm plugging in from 0 to 1. So then just copy. So I'm going to plug in 1 to begin with, subtract, and you have your answer. Just be careful when you copy it and plug in -1 and plug in 0. Number 23. Again, the most powerful thing is to try it first. And then go from there. Whoa, there it is. So the first thing I recognize is take the derivative of the denominator. So the denominator is that. So whenever I see a fraction, writing it calculus friendly is not going to help me here. I think of a logarithm. So I take the derivative of the bottom, which is 2t subtract 4. Then look at the numerator. So if I go 1/2 and multiply it, they would be the same. And then unhook the numerator, and then this is just a logarithm, which is 2t squared subtract 4t subtract 5. So just write down the denominator, and then don't forget the candy bars. Done. Number 24, that was an indefinite integral. That's why there was a constant at the end. 24 is also 1. Again, when I see a fraction, I think, all right, it could be a logarithm. But notice the powers are equivalent. So if the degree is the same here, we have to do long division to begin with. So we have to do that. Make sure you subtract properly. So the y's eliminate. So this is going to be -2 for a remainder. So then we're going to put the answer back here. So that's 1 minus 2 over. So can you write the answer? The answer is 1, and then -2 over y plus 2. That's what that is. And then just integrate each one separately. So the integration of 1 is just y. The integration of the second one, let's do it separately. The derivative of y plus 2 is 1, but we need a 2 in front so it stays the same. So it's 2, it's a logarithm, it needs the absolute value bars, and it's done. That's number 24. Number 25. What interest rate would be required for a savings account to triple in value every 20 years? So we're going to use this. So if I want to triple in value, that would mean that whatever the end amount is compared to the beginning amount, if you divide it, tripling means it's equal to 3. And we want it, how many years? 20 years. So that means that we're going to plug in 20 for t, and then we're going to solve it. And you could use your calculator. So just solve that. I don't even want to do anything more than that. So I want to solve for r. That's what I'm going to put in my calculator. So I'm going to go menu, algebra, solve. Then I'm going to type it in. 3 equals e. Remember, it's not on the bottom. It's on the left. E, the number. And the exponent is 20r. And we're solving for r. So comma r at the end. And then that would be the rate. 0.05493. And so I did that so that I could actually move the decimal 2 to the right and still have 3 decimals. So that would be the interest rate you would need to triple your money in 20 years. '26. Turn the page. In 1990, the population was 123,580. In 2000, it went up to 152,000 something. Assuming the population is increasing at a rate proportional to the existing population. So that's this situation. Assuming that, use your calculator to estimate the city's population in 2025 and express your answer to the nearest person. So I first need to find the rate of growth. So the original population was 123,580. And then in 10 years, it became 152,918. That took 10 years, right, to do that from 1990 to 2000. So I'm going to use my calculator just from that. So if I get my calculator right there, I'm going to type it in. So go menu and then go solve. Sorry, menu, algebra, solve. And then we're going to type it in. Be careful. So it's 152,918 equals, oops, I didn't mean to press that button, equals, that's the button, 123, my fingers keep pressing the wrong button, 123,580, and then it's e to the k10. Which is 10K. Okay, so comma K, and there's the rate. Now, what we're going to do is we're going to highlight over it. I'm going to go Control C. Now it's copied in my calculator. So now when it asks for in 2025, I can start from 152,918. And then it's e to the exponent. Now I'm trying to solve for the time that it would take, right? So it says in 2025. So that's in 5 years. No, 25 years from 2000. So now, and I'm going to write it down here, it's going to be 25 years later times the rate. So Control V. And then just go back and erase the equals K part. Oops. There we go. And you have your answer. And now to a whole number, that would be, make sure that's here, 260,456. Perfect. So let me make sure I wrote that down right to understand it. So we're starting with 152,918. E, we just said the growth rate, which is this. So it's about 0.021, but we did the full number. And then it's 25 years later. That's what T is. From 2000 to 2025. And then that answer was 260,456. Rounded to the whole number. All right, 27. In number 27, a radioactive element has a half-life of 1,000 years. So we can still use this for half-life. It just means that when I divide, right, in terms of, in fact, here, let's use this one. It's the same formula, but let's just use this one. So half-life means that when I divide this, it's half, right? So whatever the initial amount was divided by what it became, that's half. I need to find the rate first. The half-life is how many years? 1,000 years. So there's step number one. Then we're going to save it in our calculator. So again, we're going to go menu, algebra, and then solve it. And then it's, what is it again? 1/2 equals e to the exponent 1,000 t, right? 1,000 k. And then comma k. So that's what I'm going to save in my calculator. So move the, highlight it, go Control C. So now it's saved in there. And now we're going to use that number. So we already just found k is negative 0.000693. Then it says how much of 200 grams will be left after 750 years. So there, you just plug in the values that you have. Make sure you paste in the rate, and then we're done. So it's 200 E, and then I'm going to go 750, times paste, Control V, get rid of the K equals, and then you have your answer. So about 118.920. And it's in grams. That's how much would be left after 750 years. All right, number 28. Number 28, solve for y prime and find slopes for the solution curve to the differential equation at... use this first. Haha. We needed a diffie-q to begin with. So there's our diffie-q. Oh, and we're going to use that for a bunch of things. Okay, so there's 28, and there's our diffie-q. So what's the slope here? So it's probably helpful to get y prime by itself. So it's xy plus 2y. So get the slope formula by itself, and then just plug in the slopes. So 0, 2, what is slope does that give you? And just plug in and answer it. So I'll do it with you. So for A, the answer is just 4. For B, at negative 2, 0, so you plug in negative 2 for x and 0 for y. The slope is 0. For C, negative 1 and 1. So plug in negative 1 for x and positive 1 for y. I think it's 1. And D, negative 4, 1. Plug it into the slope formula, and the slope would be negative 2. And then E, plug in k, 0. So that would be any x coordinate, k. Put in 0 for y, and you can see that the slope would be 0 no matter what the x coordinate is. So that's the answer for 28. 29 says sketch a slope field for the equation, the one shown to the right. So it's just the second quadrant. So I'm just going to draw the second quadrant. It goes 1, 2, 3, 4. So 1, 2, 3, 4, and then 4 up, right? 1, 2, 3, 4. So 1, 2, 3, 4. And then I'll just put dots at where the slopes are going to go. So there it is. Isn't that pretty? And then, again, we're using this formula at every one. I'm going to do it in pink. So the best one to start with, or is it a different one? No. We could also factor out a y to make it easier. So the slope formula, if you factor out a y, is this. That might be easier to look at, you know? Do you see how I factored out the y? So when x is negative 2, so see here, when x is negative 2, the slope is 0. So those are just horizontal lines at 0. Should try to use the point of it a little bit more. If I look at here, like at when y is 0, that's here, we also have the same thing. So when y is 0, we have the same thing. And then we got to fill in the other ones, like at negative 1 and positive 1. So negative 1 and positive 1 is a slope 1, then it goes up to 2, and then it goes up and then up, so it rises. Here on the left, if I plug in negative 3, it's these are reflections of each other. It gives you negative 1, and then this, and then this, and then rises up. And then the last one at negative 4 and 1, it says negative 2, and then it just keeps getting steeper and steeper and steeper. So there is your slope 1. Understand the pattern and the relation connection to the slopes. Is it getting steeper? Is it staying the same? Is it 0? And so on. And then it says through which point? Do a solution curve through 0, 2. So 0, 2 would be here. So you can tell what's happening here. So once it hits negative 2, it's a turning point. And so you can get a sense of what's happening there. So follow the curve, recognize where the turning point is when the slope is 0, and then turn it, and then just follow the river, right? How it flows. That's 29. Number 30, that's number 30 was the drawing it. Number 31 is to solve the diffie-q and find that position. Use your calculator to graph the particular solution and compare it to your problem. Okay, so for 31, we're going to solve this diffie-q. So we're going to write down dy by dx equals y times x plus 2. That's it. They're going to separate the variables. So I'm going to divide by y and multiply by dx. And then I'm going to integrate both sides. So separate the variables. 1 over y is ln y. We've done so many of these. And then that would be x squared over 2 plus 2x plus c. And then at any point you could plug in the point. So which point are we plugging in again? So we're going to plug in 0, 2, right? Is that what we're plugging in? So 0, 2. So if I plug in 0 for x and then 2, c would equal... So plug in 0 for x and so on. Let me just change this just a little bit. So I'm going to write this as y by itself, e to the x squared over 2 plus 2x. That's all in the exponent. Plus c, we know to write that as times e to the c. And then to remove the bars, that we're going to rename the constant. So plus or minus e to the c will be c2. And then we're going to plug in 0 for x. So now if I plug in y is 2, and if I plug in 0 for x, you get e to the 0, which is 1. So c2 is just equal to 2. So the equation is 2 times e to the x squared over 2 plus 2x. So there's the diffie-q right there that we solved. And this is use your calculator to see how it compares to like the graph that you just did here. So let's do that quick. So on your computer, we're going to go to graph. I'm going to delete what I have here. I'm going to go tab and I'm going to type in 2. Oops. I'm going to type in 2 and then e. And then in the exponent is going to be a fraction, which is x squared over 2. Move the cursor, plus 2x. And just make sure I typed it in okay, and then enter. And then what does the curve look like? And so can you see like what we created through 0, 2, and what that is? You can see that they're pretty similar, right? In terms of what we did. It rises a bit faster, right? A little skinnier. But there's the curve. You can see that we did it correctly. All right, last one. We have 32 and 33. So we're going to use our calculator here. So we have the graph y equals cosine x cubed, and then y equals x squared, and then set up an evaluate integral that leaves it. Show the equation to find the limits of integration. All right, and compare it to your graph from there. So first of all, I'm going to do an equation. So I'm going to go algebra. I'm going to solve this. And the equations are cosine. So press the trig button and then cosine. The trig button's up here on the top right there. It says trig. Cosine x cubed equals x squared, comma x. There we go. All right. So I get negative. Let me just check my answer key to make sure that we're on track. So I get two answers. So one, I get positive and negative 0.881. Yeah, that's what that is. So excellent. And then I just need to know what's going to be on top and what's going to be underneath for that. So if I use my calculator again to graph this, I'm going to erase that. And then I have cosine x cubed. So we'll do that one first. So there's the blue one. See how it keeps going on like that. I just want to know which one's above and which one's below. So the second one is just x squared. I already have a pretty good idea of that. So the blue is on top and the red one is underneath. That's all I kind of needed to know. So the setup is going to be, we're integrating from negative 0.881 to positive 0.881, and cosine is first and then x squared is second. So that's what would give me the area between the two curves. So now I'm going to type it in. All right, so I'm actually going to highlight. How would I do that? Here, let's see if I can do it with the cursor. So I just clicked on it. And then I'm going to go Control C. So now I have it in there. Okay, so I'm going to integrate. So that's Menu, Calculus, Integrate. And then I'm going to go Control V to paste it in. Beautiful. I'm going to go Control V again, but I'm going to take away the negative. That's another way to copy paste, which I like. You got to be talented with the cursor and highlight, which I'm sure you are. You just click it and then kind of move it across and it highlights. And then what am I integrating? So I said it's cosine x cubed, subtract x squared dx, and then that's it. And it's make sure it's accurate, 1.248. Perfect. All right, last one, number 33. A particle moves along the axis so that its velocity is ln t plus 1, subtract 2t plus 1. And it says find the total distance from 0 to 2 with your calculator, right? So awesome, showing it and then answer it. So we're going to integrate from 0 to 2 the absolute value of that, and that will give me the answer. Done. That's what total distance and how you find it. So calculus, integrate again from 0 to 2. We're going to do absolute value bars. And then type in the velocities. So that's ln x plus, we're going to use x. Or we can use t. So t plus 1. Move the cursor. Oops. There. And then subtract 2t. Plus 1. And I get the total distance to be 1.540, which is perfect. All right, that's it. You did it. Thank you for doing your work with me. I'm proud of you. Mr. G Math over and out. Until next time.